Alright, today we're talking about superposition and resonance. So the first thing we're going to do is ask ourselves, what happens if I have two waves and they come together? Alright, well, usually if we have what is known as a linear medium, then the two waves, they just add together. It's like they don't interact with each other, you just get the sum of the two. They just go right on top of each other. Now, what is a linear medium? A linear medium is a good approximation to most of the wave mediums that you will meet in everyday life. We're assuming in this class only linear mediums. If you want to deal with nonlinear mediums, which is what you tend to get when you have really big waves such that the system just behaves strangely, you're going to have to learn that in another class. But assuming a linear medium, when two waves come together, their amplitudes add. We call this superposition. The two waves, we just add them together. So imagine, if you will, that I have, say, some wave medium, and I have a wave that looks like this, that's traveling this way, and imagine I've got another wave that looks like this, that's traveling this way. Alright, as time goes by, those waves are going to get closer together, right? So maybe sometime later we have a wave that looks like this. Eventually they're going to be right on top of each other. What happens? They just add together. So here's kind of where they overlap. I get a bigger wave, right? Eventually they're right on top of each other, and I just have a really big wave. And then they'll separate. And after some time, maybe I'll have, now this wave's past this one, this one's past this one. They still have a little bit of overlap, and then sometime later they'll separate out and continue on their way. So that's the principle of superposition. If I have a linear medium, which is what we're dealing with in this class, when I have two waves come together, I just add them together. Alright? Now, let's imagine, if you will, that I have two speakers that are both producing sine waves. Alright? And imagine that I am an equal distance from both speakers. They're both in front of me, right next to each other. I'm some distance away, and they're both playing the same sine wave. Alright? When the sound reaches me, I'm just going to hear the sum of both of those speakers. So I will just hear a sine wave at the same frequency, but with twice the amplitude. And of course, twice the amplitude means 4 times the power, right? So that the waves, they just add together to make a bigger wave. But what if I swap the wires on one of the speakers such that when the speaker on the left is going outward, the speaker on the right is going inward? Alright, so now if I look at the pressure waves reaching my ear, I have this. I add them together and I get nothing. So when I add them together in phase, the two waves are in phase, they're both going up at the same time, they're both going down at the same time, I get a bigger wave. That's known as constructive interference. The two waves interfere constructively. When one is going up, when the other one's going down, and they cancel each other out, that is what's known as destructive interference. All right, now, in real life, it may be harder to hear this because when we listen to, two speakers on our radio, first of all, they aren't necessarily playing the same thing, right, if we have a stereo. Second of all, they're going to be playing lots of different sine waves at different frequencies, okay? And third of all, there's reflections off of the room, so we may not get perfect destructive interference, even though we should, because maybe some reflections off of different walls do not add perfectly out of phase. And then fourth of all, our ears hear logarithmically, as we discussed before, so even if there's a little bit of sound left over, it may sound a lot louder than a plot like this would make you think. Alright, but this is a real effect that you can actually hear, and we will do it in class. Alright, and you'll hear constructive and destructive interference. Alright, now, maybe I get destructive interference because my two speakers are doing two different things. Another way we could get destructive interference is if my two speakers are doing the same thing, but I move one of them closer to me. Oh, by the way, destructive interference is how active sound cancellation works. You get those headphones that cancel out sound. What they're doing is they have a little microphone, they listen to the sound approaching your ears, and they make another sound that's out of phase with it and cancel it out. But let's go to the case where I move one of the speakers. If I move one of the speakers by half of a wavelength closer to me, even though the speakers are both moving up and down together, right, or I guess in and out together to make a pressure wave that goes up and down at the same time, because the one speaker is further away from me and has to travel further, when the two waves get to my ear, they're out of phase with each other and they cancel out. All right, so whether I get constructive or destructive interference, or somewhere in between, depends both on the phase of the speakers relative to each other and how far away they are. Now, in general, what happens if I have two sine waves? Let's say that one of my sine waves is described as A sine kx. Well, let's forget about position. Let's just look at my ear, all right? So let's just consider two sine waves. When they reach my ear, all right, one is oscillating at some frequency omega t, and the other one is at the same frequency, but maybe there's going to be different phases between them. Maybe because the two speakers are not oscillating exactly in phase, or maybe because the sound from one speaker had to travel further to get to me than the other one. All right? So they have these two different phases. If they're exactly in phase, they'll add constructively. If they're pi radians out of phase, they'll add destructively and cancel out. All right? And this could be sound from speakers. This could be light from a laser. This could be ocean waves, whatever you want. I've got these two sine waves in a linear medium. The total wave is just the sum of the two, right? Which is just A sine omega t plus phi 1 plus A sine omega t plus phi 2. Notice we're taking the simple case where both waves have the same amplitude. All right? Now, there's a trig identity that says if I add two sines, I can factor out the A. Let's do that first. So it's going to be A sine omega t plus phi 1 plus sine omega t plus phi 2. There's a trig identity that you may remember, you probably don't, but it says if I add two sine waves together, what I get is 2 times the cosine of the difference in the two. So if I take the difference divided by 2, so I take this minus this, so it's going to be phi 1 minus phi 2 divided by 2, times the sine of the average. If I average, I add them together. So I'm going to get omega 1t plus omega t plus omega t divided by 2 gives me omega t. Phi 1 plus phi 2 divided by 2 is just phi 1, phi 2 divided by 2. Okay, so there you go. So you look at this. There's my trig identity. All right, once again, the trig identity was that sine of A times sine of B is equal to 2 cosine A minus B over 2 sine of A plus B over 2. All right, so I just apply that trig identity and I get this. And what I see is I have a sine wave that's oscillating at the frequency of the two waves I added together. There is a phase on that sine wave, which is just an average of the two phases. This thing here doesn't depend on amplitude. It's kind of like this whole thing right here is the amplitude of my new sine wave that I get from adding the two of them together. And the amplitude depends on the differences in those phases. If those two phases have no difference, if they're in phase, I'm going to get a sine wave which is twice the amplitude of the two individual waves because cosine of 0 is 1, right? But cosine of pi over 2 is 0. So if these two differ by pi radians, that means my two waves are 180 degrees out of phase, right? So one's doing this and the other one's doing this. And just as we expect, we get 0 amplitude. They cancel each other out. All right? So that's what happens when I add two waves together. All right? I get another wave, but its amplitude will depend on the phases of those two waves. All right? Okay. Now, incidentally, if you ever forget this trig identity, and you remember it's a cosine and it's a sine, but I don't remember which one's the sum and which one's the difference, remember these two sine waves are equally good. Why should it be A minus B instead of B minus A? There's symmetry here, right? I mean, I can swap these two around and have this plus this instead of this plus this, and it's the same equation, right? So remember, cosine of a negative number is the same as the cosine of the positive number. So that's where you put the a minus. Sine of a negative number is negative the sine of a positive number. It matters whether the a or b comes first in the sine, only here it doesn't because we're just adding them together. So just a quick way to remember which one's the cosine and which one's the sine. Okay, now what happens when a wave reflects? Imagine I have some wave on a string and I get to the end of the string. What happens when it reflects? Imagine I have some light waves and they hit a piece of glass and reflect off. What happens to the waves it reflects? Well, let's just for now consider a string. And it depends on what happens on the end of your string. So imagine, if you will, I have a string and it's fixed at one end. Alright, so I have my string, I've got some wave going through, whatever, and it's fixed at one end. Let's have my string, and let's say there's a little pulse going through on my string, and it's traveling this way. What's going to happen when it gets to the end? If the end of my string is fixed, it can't move. I can't just have this thing just go to the end and have nothing interesting happen because, right, the string goes up with this pulse, but the string can't move. So here's what we're going to do. If I have a fixed string, I'm going to pretend like this string is actually really long and it's just fixed in the middle here. Alright, this part of the string doesn't really exist, doesn't matter, but let's just pretend that instead of having a string that ends and it's fixed, let's imagine that it goes on, but I have to have some wave coming over here that will cancel the wave coming here and always keep this end fixed. Alright? So let's imagine that. So imagine, if you will, I have on the string a pulse that looks like this, right? What do I need over here to cancel it out and make the string always be 0? Well, I just kind of need something that's the reflection of that, right? Now as these two come together, when this point hits here, this point will hit here and they'll cancel each other out, right? When this point reaches here, this point of this wave will reach there and it'll cancel out. Alright? So really I have a string. I don't really have this string over here. It's tied right here, but I'm saying, what kind of a wave do I need to inject into the string to keep this end here from moving? And this is that wave right there. So if I send in a wave that looks like this, right, what's going to come out is a wave which is going to look like this. It's the string inverted, right? So it comes in like this. A little while later it's coming out like this. So if I have a fixed end, I basically get the same wave but flipped around and upside down coming back out. That's what will reflect. So when I have a fixed end, I get a reflection which is upside down. Alright? What if I had a free end? What does a free end mean? I mean, if I have a free end of my string, I don't have any tension in my string, right? If I just have a string and it's not attached to anything, there's no tension, I don't get waves. Alright, so I'm going to make something that seems really, really artificial. Alright, and the reason I'm going to do it is because a free end for a string doesn't make a lot of sense. Alright, physically. But when we talk about organ pipes and waves in air and how they reflect, it turns out a free end makes a lot of sense. And so for now, I'm just going to deal with strings. I'm going to make some artificial thing up that sort of works if you think, well, okay, so it works for strings even, and it's totally artificial, but we'll have something analogous which is actually realistic and useful when we talk about sound waves. So here's my artificial construct I'm going to make for my free end of a string. So it can be free to move but still has tension. What I'm going to do is I'm going to have a pole with a ring that goes around that pole, and I'm going to attach my string to it. Alright? Now I'm going to assume that this pole has no friction, so the ring moves up and down with no trouble. Alright? But I'm also going to assume that the ring has no mass. Alright? So what does this mean? Alright, I can have tension in this direction, but what if the string was coming off this way? What would happen? Well, the pole only stops the ring from moving in this direction. The ring is free to move in this direction. How fast is it going to move? Well, my ring has some mass, and force is equal to mass times acceleration. Well, I said the mass is going to be 0, so any finite amount of upward force will mean infinite acceleration, right? I have to have infinite acceleration if I have 0 mass. So what does that mean? My ring is going to respond infinitely fast so that there will never be a vertical force on the ring. What does that mean? It means that as a wave comes by, the string can move up and down, but the slope of the string has to always be 0. All right? So now imagine, if you will, I have this pulse coming along, like that, and it's coming to this ring here. What's going to reflect back? What wave do I have to inject in to cancel it? Now, instead of one that is inverted, I'm going to have the same wave upright, right? So that when this piece of the wave hits, when this piece of the wave hits, we're injecting this piece of the reflected wave, and the two have slopes that are opposite, and they canceled out, and you get no slope. Right here, when this part hits, I've got 0 slope, so I inject a wave with 0 slope. Right here, I have a wave with the slope going down, so I inject a wave with the slope going up, so that my string has no slope. And the ring will move up and down, but the string will have no slope. So, once again, for a fixed end, my waves invert when they reflect. For a free end, they don't invert. All right? Okay, now let's imagine a guitar string. A guitar string has a free end, it has a fixed end. So imagine I have a sine wave coming down my guitar string. Over here somewhere, it's going to hit the end of the string and come back, right? So when I reflect that wave, I get another sine wave traveling in the other direction. All right? So on my guitar string now, I have these sine waves. I have a sine wave traveling in, I have a sine wave traveling back. Let's not think about what happens at the other end when it reflects there. Let's just have a semi-infinite string for now. Goes, reflects off of one end, comes back. Now I have two waves traveling in opposite directions. All right? So what does my guitar string do? Does it do the one or the other? Well, remember the principle of superposition. If I have these two waves, they just add together. So what will the guitar string do? It will do the sum of these two waves. When I add these two waves together, so I have the blue wave going to the left, the red wave going to the right, I add them together, I get the yellow wave. All right? Let's look at that yellow wave alone now without the two waves. So this is what my guitar string will do. So I send a wave out from infinity, it reflects and it comes back. Those two added together do this. This is what's known as a standing wave. It's called a standing wave because it's not traveling. The blue and the red waves are traveling waves. They're going in some direction. But the yellow wave isn't going anywhere. It's just oscillating. All right? Now, there are places here. Right here, notice the string doesn't move. This is what's known as a node. All right? Over here is another node. All right? And here's another node. How far apart are the nodes? If you said one wavelength, you need to think closer, right? Because here's one wavelength, right? One wavelength goes from here to here, but there's two little standing wave humps in between, all right? So the nodes are half a wavelength apart in a standing wave, all right? So a standing wave is what I get when I have two sine waves, same frequency, same wavelength, same amplitude, traveling in opposite directions. They add together to make a standing wave, all right? Now, let's use our trig identity to see if we can figure out something about standing waves. So my standing wave, I'm going to have some sine wave with some amplitude traveling kx plus omega t. That one's traveling to the left. I add one in traveling to the right. And I add these two waves together, I should get a standing wave, right? Our trig identity says that this is going to be 2 times a times the cosine of the difference of these two over 2. So if I take this minus this, I'm going to get 2 omega t over 2. Oh, so just omega t. And then we multiply by the sine wave of the average of the two. So I'm going to add them together and divide by 2. When I add them, this part will cancel out, and I'm just left with kx. All right? So this is what my sine wave looks like. All right? I add my two traveling waves together, and my standing wave then has an amplitude which is twice the amplitude of my two traveling waves, and that's what we saw, right? You look up here, the amplitude is bigger. Yep, boom, goes up twice as high. If we start, like look right here, okay, so here's 0, and this guy comes up about twice as high as those other two. In fact, exactly twice as high. All right, and that's what the trigonometry tells me. I've got an oscillating wave. It oscillates at the frequency of the two traveling waves. All right, but the amplitude, now here the sine wave's kind of acting like our amplitude. If we look at any given point and look how it oscillates, the amplitude of the oscillation depends on where we are. All right, right here in the middle where x is, let's see, where's the middle? Right here in the middle where x is 0, sine kx is 0, and I get no oscillation. But if I move over, right, if I move over a quarter of a wavelength, all right, right, here we are. So if I move over, boom, here's one wavelength. If I move over half a wavelength, sine of pi is 0, I get 0 amplitude here. But if I move a quarter wavelength from the center, sine of kx is equal to 1, and I get the full amplitude of my traveling wave. So once again, the full amplitude of my standing wave. So right here where the standing wave doesn't move, that's known as a node. Here where it's at its maximum motion is known as an antinode. All right, so the nodes are half a wavelength apart, the antinodes are half a wavelength apart, and they alternate. All right, so there is the math of a standing wave. Now, once again, I get a standing wave when I have two sine waves traveling in different directions. I mentioned you can get that from reflections. If you have a slinky, this is a great thing to do. Go attach your slinky to a doorknob, send a little sine wave in, and you'll see when it reflects off, you'll get a standing wave. You can actually see this. All right? Periodic laser potentials. One fun thing you can do in atomic physics, I'm an atomic physicist, is you can trap atoms in laser beams. If you reflect a laser beam off of a mirror, now you have two sine waves traveling in opposite directions. It makes a standing wave. And you can actually make little bunches of atoms that are trapped in the antinodes of your standing wave. You can actually do this in 3 dimensions, and you can actually make crystals of atoms where the crystal structure is not determined by the interaction of the atoms with each other directly, but by the laser field. So you can make like an array of atoms, and you can do all kinds of fun things with them, but they're not stuck together atoms, they're spaced by half a wavelength of the light. All right, also, you have reflections on the ends of a guitar string or a viola string, a piano string, and so forth. All right, and so you tend to have standing waves on guitars and violins and pianos. All right, and as we'll study later, on organ pipes. All right, now, the thing is, though, a guitar string has 2 fixed ends. All right? So when I send my wave in and it reflects, I send another wave back here, but it's going to come back and it's going to reflect here. All right? And if I put just any wavelength in, all of those reflections aren't going to add together. I'm going to have troubles. All right? So it turns out that not any sine wave can live on my guitar string. Only sine waves that have nodes, I can only have standing waves that have nodes at the ends of the string. All right? So I can have a wave, a standing wave that looks like this, a half cycle later it'll look like this, and it'll just oscillate up and down. All right? What is the wavelength? So let's say my guitar string has a length L. What is the wavelength of this standing wave? All right? Remember, the standing wave is half of a wave, right? This distance right here is just half a wavelength. So L is equal to half of a wavelength, or in other words, the wavelength of this oscillation, of this standing wave, is going to be 2L. All right? This is known as the fundamental or first harmonic of my guitar string. So I'll put a little 1 here for first harmonic. The wavelength of my first harmonic is 2L. But I can also, if I have my guitar string here, I can also have a wave which has a node at each end plus a node at the middle. Right? Okay? So that's also a sine wave, a standing wave that will fit on my guitar string. My guitar string can also support this standing wave. Its wavelength, this is the second harmonic, so I'll call it lambda sub 2. Its wavelength is just L, right? I get a whole wave here, so it's just L. I can also do one with 2 nodes in the middle of the string. It looks something like this. Boom, 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 right? All right? And this one, that's a wavelength right there. So lambda 3, this is what we call the third harmonic. All right? Its wavelength is 2/3 of the wave of the length of the string. All right, guess what? I can always add another node. So if I put 3 nodes in the middle, all right, I'll get a standing wave that looks like this that can live on my guitar string. And now the wavelength of this one is, well, it's going to be L over 2, right? Which is the same thing. Well, yeah, let's just call it L over 2. All right? Notice there's a pattern here. the wavelength of the nth harmonic is just 2L over n, right? So 2L over 4 is L over 2, right? 2L over 3 is 2L over 3. So we get these different harmonics that can exist on our guitar string. Now, my guitar does not have to oscillate in any one of these harmonics, but whatever it does can be written as a sum of all of these harmonics. My guitar string can't do any arbitrary motion because we've got to keep the ends from moving. And any motion that my guitar string can do, right, can be written as a sum of all these harmonics, right, where n goes up as high as you want. What is the frequency of the nth harmonic? Well, frequency is, let's think about this. So we said the speed of a wave is 1 wavelength per period, and wavelength is 2 pi over, well, we want to keep wavelength. We're going to use wavelength, but 1 over period is frequency, so lambda f. There we go. So f is just going to be v divided by lambda. So the frequency, the nth harmonic, is just the wave speed of my string divided by lambda sub n. But lambda sub n is just 2L over n. All right? So the frequency of my nth harmonic is just the frequency of the first harmonic times n. So if you get a spectrum analyzer that looks for the different frequencies of sound coming out of your guitar, what you will find is that you only get sounds at frequencies which are some fundamental frequency or an integer times that fundamental frequency. All right? Now, if you look really, really closely, you'll find that your guitar string isn't ideal, and these harmonics are not exactly integers times the first harmonic, but it's pretty dang close. All right? So that's what we see with guitar strings, violin strings, and as we'll see next time, it's also what you get with organ pipes. All right? There's another way to think about these. All right? Instead of thinking in terms of sine waves, which is the natural thing to do, the math works great with sine waves. As physicists, we love to do things with sine waves. But I think it's kind of intuitive also to kind of imagine this. Imagine I have a guitar string and I flick it. Ooh, I make a little flick here. All right? Let's ignore the flick going backwards. Let's just imagine I have this pulse that comes over here. It's going to turn upside down. It's going to come back. When it reflects off of here, it's going to come back upwards again. All right? Now let's imagine I flick it again. When should I flick it again such that I'm flicking it right when the pulse is coming back so that I make it bigger? Well, the time I need to wait is just the time it takes to travel 2 lengths of the string. All right? So that's going to be 2L divided by V, which means the frequency of my flicks needs to be V over 2L. Wait a minute. That's just the frequency of the first harmonic. Boom. Right there. All right? What if I flick twice as fast? Well, if I flick twice as fast, I'll make a pulse coming over here. All right? And then, while that one's over there, I'll make another one. All right? And I'll have these 2 pulses going. All right? So if I flick twice as fast, I make the first pulse, then I make the second pulse, the second time I flick. The third time I flick, the first pulse will just be coming back. And I'll just, if I flick twice as fast, I'll be making 2 pulses going around, but I'll keep making those pulses bigger. So if I flick it twice that frequency, I can also get a resonance. I can also keep making my pulses bigger. If I flick 3 times as fast, I'll get 3 pulses going around, and the 4th time I flick, I will be hitting right exactly when the first pulse comes back. The next time, I'll be hitting right when the second pulse comes back, and the next time I flick, I'll be hitting right when the third pulse comes back, and so forth. So I'll keep making these flicks, these waves, bigger and bigger. All right? So this completely jives with what we saw thinking in terms of sine waves, only now we're thinking in terms of pulses, right? And how fast we have to flick to make those pulses. All right? What if I flick at some other frequency? What if I flick at 1.06 V over 2L? All right? Well, now I'm flicking a little too fast, so I'm going to flick a little bit before my first pulse gets there, and I'm going to add another pulse. And instead of making this pulse bigger, I'm going to make another pulse kind of right in front of it. All right? And as time goes by, I'm going to make lots and lots of pulses. Eventually, I'm going to have lots of pulses, and one of them is going to be coming back this way when I flick, and I'm going to cancel it out. I'm going to take it out instead of putting a new pulse in. So if I flick at the wrong frequency, eventually I stop putting energy in the system. Sometimes I flick and I'll make a pulse bigger, but sometimes I'll flick and I'll make a pulse smaller. And so on average, I'm not putting any more energy into the system. I don't have a resonance. But if I flick at one of these frequencies, it's a resonance, and every time I flick, I put more energy into the system, and the oscillations get bigger and bigger. All right, so there's an analogy to that and our sine waves. Sine waves are very different types of waves, but I can do exactly the same thing. Instead of thinking in terms of, I'm going to flick the string at some time, what I'm going to do is I'm going to maybe have a magnet that I move in and out sinusoidally to put energy in the string at certain times. If I move my magnet sinusoidally at the frequency of the first harmonic, I'll get a big sine wave, I'll generate a big sine wave at the first harmonic, and as I keep doing that, it'll keep getting bigger and bigger. If I do it at twice that frequency, I'll start exciting the second harmonic, and as I keep doing that, it'll get bigger and bigger. All right? So there's an analogy there. So that's how resonance is related to superposition, right? We had to talk about the reflections at the end. So resonance happens because of reflections. And those reflections make a standing wave, but only certain standing waves will satisfy both of our boundary conditions. And so that's where the resonance in our guitar string comes from. That's why when I pluck a guitar string it makes a certain sound. It's because of reflections and superposition and standing waves that force certain resonance frequencies.